previously, so you can find them in our linear algebra playlists if you need an extra information or more training about getting either the quadratic forms or getting the Hessian relative to our quadratic forms, as you can see. So it's really very simple, as I told you. Then for the quadratic forms, there are polynomials that only have terms of 2, exactly the same as I told you. So for this guy, it's going to be 1, 1, negative 1, and negative 1. That's the quadratic form in the matrix notation. For this guy, it's a similar debate. It's going to be negative on the principal diagonal, negative 2, negative 1, negative 3, and 1 in the 3, 1 position, and 1 on the xz, and the z of x, and the rest of the elements will equal to 0. This slide just only for more training, as you can see. Now for qx, if the quadratic form, all of it is greater than 0 for every x belongs to a set at 0, then qx is a positive definite quadratic form. The identification of the type is really very important. If q of x, the quadratic form, for every point is less than 0, then qx is a negative definite quadratic form. If q is greater than or equal to 0 for every x and it is null sum of them, it is a positive semi-definite. And same applies if it is less than 0 and equal to 0 at some points, it's going to be semi-definite quadratic form, as you can see. If q of x for some points is greater than 0 and other points less than 0, then it is going to be indefinite quadratic form. That's the main classification, and as I told you, we already did go through this plenty of times. Also, I want to add the classification of quadratic form using the principal minors, and this is what I'm going to depend on. So this slide and the coming slide are really very important for you to watch and to understand. Please review these remarks. If all the principal minors of A, we will go through the principal minors shortly, are positive, then remember this is going to be a positive definite quadratic form. If the principal minors, and this is really very important, if the odd ones are negative while the even ones are positive, then in this case you will have negative definite. Look how it is written. If the first principal minor is less than 0, the second is greater than 0, the third is less than 0, which means if the odd order principal minors was less than 0 and the even order principal minors is greater than 0, then you will have a negative definite. Okay, if all minors of A are greater or equal to 0, and at least one of them is 0, then it is a semi-definite case. I'm not going to study it. If exactly the same, these are the semi-definite cases, I'm sorry. If all minors of A of even order are greater or equal to 0, all the minors of A of odd orders are less or equal to 0, then at least one of them, then Q is a negative definite. As I told you, these two cases, we are not going to study them in our analysis. And if some of the minors doesn't follow the rules that we spoke about, so it is indefinite quadratic form. So once more, those are the main definitions, or how to classify your quadratic form according to the principal minors, as you would say. So once more, if all the principal minors of A are positive, then it's a positive definite quadratic form. If the principal minors of A alternate in sign, but the odd ones are less than 0, the even ones are greater than 0, then you have a negative definite quadratic. As I told you, we are not going to talk with the semi cases. If none of the other condition is happening, which means if this is broken, which means if you have the odd is greater than 0 or it doesn't apply exactly, then you have indefinite case. Remember the principal minors, how to evaluate them. So if this is a matrix and I'm searching for the leading principal minor, all I have to do is to try to get the determinants, on the principal diagonal one by one. So that's the first of them. This is A1. That's the first principal minor of degree 1. And then I will take 2 by 2. And that's the second principal minors 2 by 2. And increasing each time a row and a column and the row till you get the end of your matrix. That's the third order and so on. Those are the leading principal minors, but we call them here principal minors according to our slides. And depending on this, I will try to determine and classify. So let's go through this, trying to classify this problem. He wants you to classify the quadratic form given by x squared minus 2 of an xy plus 2y squared, which means all I have to do now is to get my easier matrix. So I will start these steps by getting the principal minors of my quadratic form. The quadratic form is going to be, as I told you, 1 on the principal diagonal, 2 on the element 2, 2, and then negative 2 I will divide into half of it in xy and the half of it in y of x. I will take this matrix and try to determine the determinants of the principal leading minors. So the first principal leading the minor, in this case, it's going to be 1. So the determinant, okay, the first minor is going to equal to 1. The second minor is going to be all of it. 1 times 2, of course I'm multiplying the elements on the principal diagonal, 1 times 2, minus negative 1 times negative 1. So it's going to be 2 minus 1, which is also positive 1. So for the minors over here, the principal minors, this is for A1, which is the first element only, and this is for A2, which is a 2 by 2. 1 times 2 is equal to 2 minus 1 is also positive 1. Both of them are positive values. Since both of them are positive values, as you can see, so it's a positive definite quadratic form. Here I've classified the type of the quadratic form. So once more, as they are all positive, we conclude that the quadratic form is a positive definite quadratic form, as you can see. It's really very simple, steps direct, there is no problem whatsoever. So first of all, get your quadratic form, get the principal minors, compare, and according to our classification. Let's do it once more. Once more, if I have negative 2 over x squared, 4 of xz, this is a 3 by 3, okay, because I have z, minus 3y squared, minus 5z squared. So the first step is to try to get my matrix exactly the same. This is the element 1, 1. That's the element 2, 2. That's the element of z. Then I have xz, I will divide it by 2. 2 on the first and third position, the other half on the third and the first position, as you can see. The rest of the numbers are zeros. Now I will try to identify the principal minors. I will have 3 principal minors. The first degree, okay, or the determinant A1, it's going to be the first element on the principal diagonal, which is going to be a determinant of negative 2, just only this number. Then the determinant of A2, I will take 2 by 2, which is negative 2, 0, 0, negative 3. And then the third principal minor is going to be simply all of it, which is negative 2, 0, and 2, 0, negative 3, and 0, 2, 0, and negative 5. I will try to evaluate each one of them to identify the value. So the value of the determinant of negative 2 is negative 2. The value of this determinant, negative 2 times negative 3, it's going to be positive 6. I will go to this one, the third one. Negative 2 times negative 3 times negative 5, which is going to come up to negative 30, according to Sarah's rule. 0 times 0 times 2 is 0. 0 times 2, 0 times 2 is also 0. Then I will have the negative of 2 times negative 3, which is going to be a negative for a 12. That's is going to come up to negative 18. As you can see, the principal minors of odd order, the principal minors of odd order is less than 0, while the principal minors of even order is greater than 0. And in this case, I'm dealing with a negative definite quadratic form. So you have to understand very well the classification and then follow it as I told you. So once more, this is A1, which is negative 2. This is A2, which is the 2 by 2 set, as you can see. And that's for A3, the evaluation of the whole determinant, which is negative 18. The first and third, which are the odd ones, are less than 0. The even order is greater than 0. So it is already the rule is applied, as I told you. And in this case, we are talking about negative definite quadratic form. Another example I wanted to give to you, which is negative 2x squared for an xy plus 3y squared. That's our quadratic form. And once more, I want to classify it. The first is negative 2, as you can see. The second is negative 10. Now the rule is broken. So it's for an indefinite directly, as you will see. It's an indefinite quadratic form. According to the definiteness of your quadratic form or Hessian matrix, I will be able to classify my critical points. This is why we did this revision, as you can see. So, for example, if I have the problem let's get back again to our analysis, and this problem contains 2x squared, y squared for z squared minus x plus 2z. And I want to search this problem for optimality. And of course, it's a non-constraint since you don't have any constraints about this problem. So I would start by getting the gradient vector and putting it equal to 0. Or finding the first differential and putting the first differential equal to 0. So I would start with differentiating with respect to x, with respect to y, with respect to z, and equal to 0. If we start differentiating by relative to x, this is going to be a 4 over x. Then differentiating with respect to x, this is going to be negative 1. I will take the first derivative with respect to x and put it to 0. Let's get the first derivative with respect to y. This is going to be 0. That's going to be 0. Zeros. It's just only 2y equal to 0. Getting the third derivative equal to 0. Those are zeros. This is 8z plus 2 equal to 0. This is exactly what happened. From the first one, x is equal to 1 over 4. From the second, y is equal to 0. From the third, z is equal to minus 1 over 4, as you can see. So the critical point at the time being is a quarter, 0, and the negative 1 over 4. That's the first point, or the stationary point, as you can see. That's my stationary point that I will need to analyze in order to know if it is a critical point or it is a saddle point or inflection point. The second step is to get my differential. In order to get a differential, for this case, I will have to complete a Hessian matrix. I will have to complete my Hessian matrix, as you know. So in order to do this, I will need to complete my Hessian matrix. So simply, all I have to do at the time being, all I have to do in the time being is to try to get my Hessian matrix, which is gonna be, in this case, is gonna be partial 2f partial divided by partial x squared, partial 2f partial x partial y, partial 2f partial x partial z, partial 2f partial y partial x, partial 2f partial y squared, partial 2f partial y partial z, partial 2f partial z partial of x, partial 2 of an f partial z partial y, partial 2f partial z squared. I will need to get the values of my homogeneous, as you can see, my Hessian matrix. Very, very simple. Okay, this is the first derivative, which is for x minus 1. So I will differentiate 4. So this value is going to be 4. Then I will differentiate f, the first derivative with respect to x, but in the direction of y, which is going to be 0. Differentiating the first derivative with respect to 0, to z, which is going to be equal to 0. The second derivative, differentiating with respect to x, is 0. With respect to y, it's going to be 2. With respect to z, it's going to be 0. Differentiating with respect to x is going to be 0. Differentiating with respect to y is going to be 0. Differentiating with respect to z is going to be 8. And that's my Hessian matrix. That's what I am going to do at the next step. So once more, I'm trying to get the second differential, which is going to be, as you can see, 4 double zeros, z2 zeros, double 0 8. I will need to get my Hessian matrix at the critical point, which is a quarter, 0, and the negative 1 over 4. Since my Hessian matrix doesn't have any variables, so it is the value at a quarter, 0, and the negative 1 over 4. That's the value of my Hessian matrix. Now I need to identify, okay, I need to identify or to classify this Hessian matrix. Is it a positive definite, negative definite, or indefinite in the cases that, in the 3 cases that we will study this year? So I will have to get my leading principal minors, which are 4. That's for the first of them. Here we go. That's H1, which is going to be 4. H2, which is going to be the determinant 2 by 2, which is 4 times 2. It's going to come up to an 8. And the whole, as you can see, it's a diagonal matrix. So it is the multiplication of the elements of the principal diagonal. The 3 minors are greater than 0. And once the 3 minors are greater than 0, then I'm dealing with the case of a positive definite. Since we are dealing with a positive definite Hessian matrix, okay, at the point a quarter, 0, and the negative 1 over 4, so it's greater than 0, so f represent a local minimum. So if I have positive definite, then it's a local minimum. If I have negative definite, then I will have a local maximum. And so on. The coming problem, it's 2 minus x squared minus y squared. I believe that's an equation of some type of paraboloid. Okay, so once more, all I have to do now is to get my first derivative equal to 0, which means I will get the gradient vector. So differentiating with respect to x, it is a repetition of the main steps. It's going to be negative 2x equal to 0, negative 2y equal to 0. So here is the partial derivatives equal to 0. It will give you negative 2x equal to 0, negative 2y equal to 0, which will lead to that the point 0 and 0 are the critical point or the probable critical point. Then I will get the Hessian matrix. The Hessian matrix in this case is going to be partial 2f partial a 2 by 2 matrix, as we did previously. So it's going to be partial 2f partial x squared. It's going to be the derivative of this function with respect to x, which is negative 2. Differentiating the first derivative with respect to y is going to be 0. Differentiating the second, the first derivative with respect to x, it's going to be 0. Differentiating with respect to y is going to be negative 2. And also, once more, the Hessian matrix doesn't depend on the value of your critical points. So it's going to stay this manner. If you remark, the first leading principal is negative, okay? And the second leading principal is going to be positive. Negative 2 times negative 2 is going to be positive 4. And this is exactly like what we studied. If we are dealing with odd principal minors, less than 0, and even principal minors is greater than 0, this represent the case of negative definite Hessian matrix, which will represent, as you can see, a local maximum at this point. طبعا steps is really very simple. Each step delivers the second step. There is no problem whatsoever. It's really very simple, smooth, but mainly you will have to memorize the how to identify the difference of or how to determine your Hessian matrix. There is another simple scheme we will see inshallah after I leave this problem. So for this problem, similar results. I have just only 2 x's, so I will get also the first derivatives equal to 0. That's my first step, which is the gradient vector. I will put it into 0. So that's the first derivatives. With respect to x is going to be 4 of x plus 2 of y is equal to 0. Then I will differentiate with respect to y, so it's going to be 6y squared. This is 0. This is going to be a 2 of an x, as you can see. Trying to equate them. The problem with solving these equations, sometimes they are nonlinear as those ones, in which we will depend on the substitution from one of them into the other. So all I have to do is to substitute from the first into the second equation, and already did. So now I have y is equal to negative 2x, and after the substitution I can take x as a common, leaving me with a probable 2 cases. Either x is equal to 0, and this will deliver y is equal to 0, or from this guy, x is going to equal to negative 1 over 12. If you multiply it by negative 2, this is the second way. So I have now 2 possible stationary points or 2 possible critical points. In a similar debate, I will get to the next step. Similar debate to the previous problem. I will get my Hessian matrix once more, which means I will need to get the second derivative with respect to x, the second derivative with respect to y, the second derivative in x, then in y, or vice versa. And this is exactly what I did. Differentiating with respect to x once more, it's gonna be 4. So the first element in my Hessian is gonna be a 4. Then differentiating with respect to y, it's gonna be a 0. Then differentiating with respect to y, it's gonna be 2. This is why this element is equal to 2. In a similar manner, differentiating with respect to x, it will develop 2. Here we go. Differentiating with respect to y is going to be a 12 over y. And in this case, now I can find that my Hessian depends on the value of y or a value of x. It will change based on the critical point that you are studying. This is why I will make 2 substitutions. The first of them at the point 0 and 0. The second of them is going to be at negative 1 over 12 and 1 over 6. So the first at 0 and 0, the second at negative 1 over 12 and 1 over 6. If we make a substitution at the origin, the first leading principal is going to be 4. But the second leading principal is going to equal to, as you can see, negative over 4. And that's the opposite of what should happen. So at the origin, we are not going to have a critical point at the origin, as you can see. At the origin, just a sec, at the origin, these are the principal minors, so it's going to be an indefinite quadratic form, which should develop a saddle point. I need to do exactly the same, but at the point, not 0 and 0, the other point. So if I start substituting into 1 over 12 and 1 over 6, this is going to be 8 minus 4, which is a positive value, which means your principal minors are both of them greater than 0, as you can see. As they are both greater than 0, so I'm dealing with a positive definite case, and it will develop a minimum point, a local minimum, as you can see. Once more, the classification is clear. It's an arranged steps, systematic, very smooth, but you have to memorize the classification according to the principal minors that we already reviewed together. Okay, that's another algorithm I can use. It's also very direct one, and it depends on identifying the first derivative, the gradient vector equal to 0, getting the Hessian matrix, and according to the determinant of Hessian matrix, which is going to be, I believe, benefitable for the people who doesn't feel comfortable around the principal minors and so on. Let's see the steps. The first step is to compute the first partial derivatives, the gradient vector, put them exactly like the previous steps, put them equal to 0. So this is going to be the critical points once you have your first partial derivatives equal to 0. Then I will get the Hessian matrix. Those are critical points. The Hessian matrix is going to be very, very simple. I will have to get the second derivative with respect to x, second derivative with respect to y, and the mixed derivative. As you can see, those are the three derivatives, second order. Then I can arrange them in my Hessian matrix, f double x, f of xy, f of x, f double of y. I will evaluate the determinant of this matrix. And that's what I call it D, which is f double x times f double y minus f of x times f of y, since they are equal to each other. So it's going to be f of xy to the power of 2. Then I will substitute by my point, the critical points. If this value is greater than 0 and f double x is greater than 0, then I will have local minimum. If this value is greater than 0 at your stationary point, but f double x is less than 0, I will have a local maximum. But if your definite or your determinant is less than 0, then you will have a saddle point. If it's equal to 0, it will need an extra analysis, and that's the case that we already cancelled in our principal minors technique. So once more, if this is my problem, this is f of xy, x squared plus y squared minus 4 of x plus 6 of y, and I need to do the algorithm, it's going to be exactly the same. Get the first derivative of this function, which means it's going to be a 2 of an x minus 4 for the first derivative in direction of x, then 2y plus 6 in the f sub y. Both these two equations into zeros, you will get the critical point. So I probably have a critical point at 2 and the negative 3. I will get the second derivative, differentiating with respect to x, with respect to y, the mixed derivative, forming the Hessian matrix. So all I have to do now is to just substitute by the Hessian matrix 2, 2, 0, 0, according to the Hessian matrix. Evaluating 2 times 2 times 2, which is going to be 4, minus 0, as you can see. So the Hessian is greater than 0. F double x is greater than 0. So this point is going to be a minimum point, as you can see. That's another problem. Also, see, it's really very quick. I didn't have to go through evaluating the principal minors or something like this. Here, he wants you to find the extreme points of x squared plus y squared plus 3 over an xy. So similar steps, this is f sub x, f sub y, both equal to zeros. I have two equations in two variables. Solve them. Once you try to solve these two equations, they will develop that the critical point is the origin. Get the second derivative, is going to be 2 and 2, then the next derivative is going to be 3. I will formulate my Hessian matrix. Once more, I will multiply the diagonal matrix, the diagonal elements, which is going to be 4, minus 3 times 3, which is going to come up to negative 9. So D is less than 0, as you can see, which will develop an inflection point or a saddle point. Same debate can be, same procedures like the previous problem can be applied also to identify. That's another problem, y squared minus x squared. In a similar manner, get the first derivatives, put them equal to 0. I think the critical will happen, or the supposed to be critical at x equal to 0 and y equal to 0. Okay, so once more, this is the origin. Start to get the second derivative, which is going to be f double x, f double y, f of xy from my Hessian matrix. start to substitute. It's a negative 4. Okay, so once more, it's gonna be this is a 0 at the origin, so it's a saddle point, as you can see, and that's the shape of the hyperbolic paraboloid that we are dealing with in this slide. Steps are really very clear, very smooth, either in R and also in R2 if I'm talking about functions in 2 variables. That's another problem, but I've tried to solve this problem using the principal minors. It's a straightforward phenomena, steps. Get the first derivative, put it into 0, try to solve your equations. You have 2 points, either 0 and 0, 1/3 and negative 1/3. Get your Hessian matrix, start substituting. In this case, the odd is negative and the even is negative. And so this point is a saddle point because the rule doesn't apply. If I make the substitution at 1/3 and negative 1/3, the first is greater than 0, the first H1. The second is greater than 0, so it's a positive definite, so I have a local minimum, as you can see. Also, you have another problem, exactly the same, just evaluate using the determinants in order to find delta 1, delta 2, and delta 3. And in this case, this is positive, that's positive, that's positive, it's a positive definite, so it's a local minimum also with the similar steps, just only in a 3x3. Remark how we solved these problems, these equations together. We used this substitution, and from of them we got y is equal to 0, x is equal to 0, z is equal to 0, so the critical point is determined 0, as you can see. It's very, very simple. Okay, how to find an absolute extrema of 2 variables. In this case, I'm not going to go further, but I will give you the formula. In this analysis, I will have to have a closed contour. According to the Weierstrass theorem, if we have a compact closed boundary, we already did go through this if you remember previously, then we will have a maximum point belongs to my domain. So if I need, in order to discuss the case of absolute extremes, I will have to do the previous analysis to get the critical point or the strinary point inside my domain. Then I will have to check the values of the function at the boundaries and check what's if there is a local, an absolute maximum or an absolute minimum. So mainly this is the flow chart. I've tried to put it for you. So this is the steps to identify absolute. Determine, as I told you, the nature of your domain, open, closed, bounded. Find the critical points, f of x equal to 0, f of y equal to 0. Classify critical points as we already considered. Analyze the boundary, as I told you. Okay, analyze the boundary if they use Lagrange multipliers, but we didn't go through this, as I told you. Compare all values, find the global maximum or minimum. So these are the main steps. Once more written to you. I've already sent you this slide also to be with you in your records. And that's once more the steps. Find the critical points in a quick. Find the value of the function at the boundary. Calculate f of x, and then start to look if it exists an absolute maximum or absolute minimum. If your domain is an open set, you don't have to. One of the absolute maximum is going to be the interior, the critical. One of the local maximum is going to be the absolute, and one of the local minimum is going to be the absolute minimum if your boundary is open or unbounded. Once more, this is really look very tempting problem from our workbook. He wants you to classify this function, so a similar debate will be done, just getting the gradient vector equal to 0 once more. So it's going to be -2 of an x, -2 of a y, okay, plus 2 equal to 0, that's for the first equation. For the second equation, it's going to be negative 2 of an x and negative 8y, as you can see. I will try to solve two equations in two variables, solving them by substitution or whatever you like. Now I got the points x is equal to 4 over 3 and y is equal to minus 1 over 3, which is the probable critical point. Then start getting your Hessian matrix from the second derivative of this function. So I will differentiate once more in order to get my Hessian. The first derivative with respect to x is going to be negative 2. With respect to y is going to be negative 2. With respect to with respect to x is going to be negative 2. With respect to y is going to be negative of 8. Evaluate or classify the type of this Hessian matrix, or evaluate the determinant and compare. They are exactly the same. I'm getting the principal minors of this guy, which is going to be an even, then the second is positive, so it's a negative definite. Once it is a negative definite, this is going to represent a maximum, a local maximum, as you can see. But I want you to go through those problems. It is in the proposed exercise for the first part of our optimization. Tomorrow, if we got time, I will go through optimization with equality constraints. And as I told you, inshallah, we will go to optimization with equality constraint next time. Fair enough today for this amount, and then we'll continue next time. The last thing, this part is not gonna be exist in our next midterm. It's gonna be in our third midterm, inshallah. Thank you very much for listening and for attending today. And as always, I wish you the best. Please try to resolve these problems using your hand, because trying to solve more than one exercise, it enhances your skills and help you a lot to fix the information in your mind. Thank you very much, and I will see you next time, inshallah. Thank you all. Bye-bye.